All right, a little bit of summary in the notes here. So really what we're saying is A of t, the acceleration vector, can be broken up into, if you've ever taken linear algebra, this A of t would be called a linear combination of t, the unit tangent vector, and n, the unit normal vector. That means it's a scalar multiple times, it's a scalar times t plus a scalar times n. That's what all it means to be a linear combination of two vectors. So A of t then, the big result is A of t can be written as a scalar times t plus a scalar times n. A sub t, I already said it, but it's written here, is the tangential component of acceleration. And it really is a scalar. If you wanted the vector component, you'd take the whole thing. The vector component, the tangential vector component of acceleration would be A sub t times t. And then A sub n is the normal scalar component of acceleration. And if you wanted the vector component of acceleration normal or perpendicular to the direction of motion, you take A sub n times the principal unit normal vector, the whole thing. Okay, so those are just definitions for you. Okay, note number 2. A sub n is this guy. That's what we just derived. So it tells us A sub n is a function of both speed and curvature. You've all been in a car, maybe traveling fast around some wiggly turns, right? And you can experience straight line acceleration, but you can also experience acceleration due to turning, right? Around a curve. And what this tells us how much normal acceleration, perpendicular acceleration you can experience around a curve. But let's use a little common sense. If you're traveling in a car, so here's a curve. If you're traveling in a car, and so maybe this is a city street instead of a windy road, and you turn right fairly quickly, and maybe you're driving, you're going to feel force pulling you in that direction, right? That's the normal force that you're feeling. And the point I want to make here is, why do we have to slow down around curves? So you don't flip over or have an accident, but why? Well, look, I'll just say it this way, for constant curvature, so assuming k is not changing, for constant curvature, if you double the speed, what's going to happen to the normal scalar component of acceleration? It's going to quadruple because of its ds dt squared, right? So I'll say it this way. You double your speed, you'll experience 4 times. Okay, you double your speed, you're squaring 2 times 2 squared is 4. So you'll experience 4 times the normal component of acceleration. So it's a way to quantify why you feel pulled to the side of your car if you turn fast. Another thing that A of t equaling a linear combination of t and n tells us, the fact that A of t equals A sub t, t plus A sub n, n, that tells us that A, t, and n lie in the same plane. Whether R of t graphs to be a curve in space or in the plane, the acceleration vector will lie in the same plane as t and n. How do I know that? Based on just this formula. Well, it's really just the idea of the triangle law. Remember when you add 2 vectors, whether you're in space or in the plane, you get another vector that's in the same plane as the 2 vectors you started with. They form a triangle, right? So let me draw a picture to show you why that has to be so. So there's C. And let's say the curve is traveled in this direction. There's the orientation. So from left to right. And let's look at this point right here. And let's just draw in the unit tangent vector. So let's say the unit tangent vector is that guy. Does that look tangent? Close enough? No, you know what? Let's do it this way. Let's call this the guy. Let's draw in the acceleration vector. It'll be easier if we start with the acceleration vector. Now, does everybody see why the acceleration vector has to be pointed that way? So for the sake of argument, let's say that's the acceleration vector. That's A. It has to be pointed in that direction because it's going to be pointed in the direction that the object is turning. Remember, we think of this curve that R of t might generate as a path traveled by an object, right? So the acceleration vector has to be pointing in the direction that the curve is bending, right? So A of t would be something like that. Then what this little equation says right here, what this little formula says here, well, okay, we know which direction t is headed in. We know that it's tangent to the curve. So let's draw t. I'll draw t in black here. But actually, I don't want to just draw t. I want to draw the part t times a sub t. So I'll draw a tangent vector. And I might have to adjust that. But for now, let's call that a sub t times t. So the vector in black is a sub t times the unit tangent vector, or unit vector in the direction of motion. And then the claim that I've been making all along is that n, I've been claiming that n will point, n has to be normal to the curve, but it also has to be normal to t, doesn't it? So the claim is n would have to point in this direction as opposed to pointing, so this is another normal vector to the curve and to t, but it's not the right one. The principal unit normal vector, it's going to be that one. So that this guy is a right angle right here. And so that guy in green is n. Well, okay, it's not quite n, sorry, it's a sub n times n. Which is a scalar multiple of n, right? So according to this formula then, we derive this formula, we know that if we add a sub n times n, a sub t times t, we get the vector in blue, we get a. That's what this formula tells us. So let's do it visually. Triangle law, let's take a copy of a sub n times n, put its tail on the tip of a sub t times t, and if I weren't just doing this, well, I wouldn't call it freehand, but if I weren't just doing this haphazardly, then this acceleration vector would be perfectly on the tip of the vector in green right there by the triangle law, right? Oh, so the vector in green, the vector in blue, and the vector in black, in other words, a sub n times n, a sub t times t, a, have to all lie in the same plane. It's the triangle law, right? So even if we're in space, t and n and the acceleration vector lie in the same plane, which is interesting. In the next video, we'll use this picture to help us believe that a sub t is equal to the acceleration vector dotted with the unit tangent vector, and that a sub n is equal to the acceleration vector dotted with the principal unit normal vector.